Welcome to the fifth lecture on the category of vector spaces titled Linear Spans. Let's review our previous lectures. A subspace W of a vector space V over a field K is a non-empty subset of V such that for any scalar lambda and for any two vectors x and y in W, lambda x plus y is again in W. Such a subspace is a vector space over K in its own right for the operations induced by V. If phi is a linear map from a vector space V to a vector space W, then the image of any subspace of V by phi and the preimage of any subspace of W by phi are subspaces of W and V respectively. In particular, the kernel of phi, defined as the preimage by phi of the singleton 0, is a subspace of V. The kernel of phi is the singleton 0 if and only if phi is injective, and the range of phi is a subspace of W. If E and F are two subspaces of V, then their sum is also a subspace of V. In this lecture, we are going to study the structure of the set of all subspaces of a vector space and introduce the notion of the linear span of a subset of a vector space. Let's begin by proving that arbitrary intersection of subspaces are subspaces. Formally, let V be a vector space. If script V is a non-empty set of subspaces of V, then the intersection of script V is again a subspace of V. To clarify our notations, if E and F are two subspaces of some vector space V, and if script V is a pair EF, then the intersection of script V simply means the intersection of E and F. However, in our theorem, script V could be infinite. Let's prove our theorem. We are going to use the characterization of subspaces. Let x and y be two vectors in the intersection of script V, and let lambda be a scalar. If W is an element of script V, then on the one hand W is a subspace, and on the other hand W contains x and y. Therefore, it contains lambda x plus y. Since W was an arbitrary element in script V, we have shown that lambda x plus y is in fact in the intersection of script V. Moreover, every subspace of V must contain the zero vector. Therefore, any element of script V must also contain the zero vector, and thus the intersection of script V contains 0. This concludes our proof that the intersection of script V must be a subspace of V. Let's now introduce the central notion of a subspace generated by a subset. Let A be a subset of a vector space V. The span of A, or the subspace generated by A, is the intersection of all the subspaces of V that contain A as a subset. I emphasize that A here is only assumed to be a subset. It could even be empty. It does not need to be a subspace. In fact, the whole idea is to construct a subspace out of A. Let's make some observations on this very important concept. First, note that there exists a subspace of V containing A, namely V itself. Therefore, by the previous theorem, we proved that indeed the span of A is a subspace of V. By construction, it's easy to check that A is in fact a subset of the span of A. So the span of A is itself a subspace of V containing A, and in fact it's the smallest such. To see that, note that if you take W a subspace of V containing A, then it is a member of that set highlighted in red, and therefore by definition of the intersection, the span of A is a subspace of W. Moreover, the span of A being a subspace of V and containing A is a member of that red set. Therefore, it is the smallest element of that red set. As a matter of terminology, if we have a subset A of V, where V is a vector space, which spans all of V, that is, the span of A is all of V, then we call A a spanning set for V. I'm now going to ask you to pause the video to work on a simple exercise. I would like you to prove the following. Let V be a vector space over a field K. If X is some vector of V, then the span of the singleton X is given by the set of all lambda times X for lambda varying over all the scalars. This is denoted typically by K times X. We now look at the example that was the exercise before. I'm going to give you the proof. So the result tells us once again that if you have a vector in V, let's call it X, the span of the singleton X is equal to all the multiples of X. Let's prove this using all we know about spans, which is basically just the definition and a couple of simple observations. First of all, X is an element of the span of X, since if you span A, for any set A, then A is a subset of the span of A. So X is an element of the span of X, and the span of X is a subspace of V. Therefore, it must contain all the vectors of the form lambda times X for any scalar lambda. So in particular, we prove that K times X is a subset of the span of X. That's one inclusion. On the other hand, K times X, it turns out, is a subspace of V itself. Let's see that. If you take Y and Z element of K times X, then by definition, there exist as two scalars, lambda and mu, such that Y is lambda times X, and Z is mu times X. If you take any other scalar, call it T, then Ty plus Z is easily calculated to be T lambda plus mu times X. And that is, by definition, a vector of K times X. Since 0 times X is 0, therefore 0 is an element of K times X, in other words, K times X is not empty, we have shown, again by characterization of subspaces, that K times X is a subspace. So K times X is a subspace of V, and since X can be written as 1 times X, X is an element of K times X. But span of singleton X is the smallest possible subspace of V that contains X. Therefore, we get the inclusion that the span of the singleton X must be a subset of K times X. In blue, we have highlighted the two inclusions we needed to conclude that our example is indeed correct. So we can calculate the span of one vector. Now, let's have a look at the fundamental properties of the operator span. You should think of span as a function on the power set of a vector space. Let's fix V a vector space over a field K, and let A and B designate two subsets, arbitrary subsets of V. Then, first of all, as we already seen, the span of A is the smallest subspace of V containing A. Second of all, the span of the empty set is a singleton 0. Any subspace of V is closed for the operator span, by which I mean if W is a subspace of V, then the span of W is actually equal to W. Span is idempotent. The span of A is a span of A. Span is monotone. If A is a subset of B, then the span of A is a subset of the span of B. The span of the union of A and B actually equal to the sum of the span of A and the span of B, but the span of the intersection of A and B is only a subset of the span of A intersect the span of B. I would like you to pause the video and try to prove this theorem for yourself. Let us now prove our theorem. The first bullet point was already covered by the simple observations we made after the definition of span. Now, let's look at the span of the empty set. Of course, the empty set is a subset of any vector subspace of V, so in particular, the empty set is a subset of the singleton 0, and the singleton 0 is the smallest subspace for inclusion. So by the first bullet point, we can conclude that indeed the span of the empty set is the singleton 0. Now let W be a subspace of V. In particular, using the first bullet point, we see that W is a subset of the span of W. That's always true. But on the other hand, we make the following simple observation. W is a subset of itself, and it is a subspace. Therefore, since the span of W is the smallest subspace of V containing W, and W is an example of such a space, the span of W is a subset of W. By double inclusion, we've proven that the span of W is indeed W. Therefore, the span of A being a subspace, the span of A must be the span of A. Now, let's prove that span is monotone. So I give the additional assumption now that A is a subset of B for this bullet point alone. Well, we have that A is a subset of B, but we have, because of the first bullet point in my theorem, that B is a subset of the span of B. And span of B is a subspace of V. So span of B is at once a subspace of V, and it contains A. Therefore, in particular, it must contain the smallest subspace of V containing A, that is the span of A. And that gives us our proof. Let's now turn to the relationship between span and unions. The span of the union of A and B should be the sum of the span of A and the span of B. So note that A is a subset of the span of A, B is a subset of the span of B, therefore A union B is a subset of the union of span of A and span of B. But the union of span of A and span of B is in turn a subset of the sum of the span of A and the span of B. Therefore, A union B is a subset of the sum of span of A and span of B. So, on the other hand, the span of A plus the span of B, that's a subspace. That's the whole point of summing subspaces. So we can conclude that the span of the union of A and B must be a subset of the sum of the span of A and the span of B, because the span of A plus span of B is a subspace on one hand, and it contains A union B on the other, so it contains the smallest subspace containing A union B. That's the span of A union B. Now, for the converse inclusion, let's pick an X element of the sum of span of A and span of B. So, what does it mean for X to be in that sum? It means that X can be written as little a plus little b, with little a in the span of A and little b in the span of B. That's the definition of the sum. But you see, A is a subset of A union B. Therefore, by bullet point right above, span of A is a subset of span of A union B. And so little a is an element of span of A union B. And for a similar reason, little b is an element of the span of A union B. Therefore, I was able to write little x as the sum of two elements, both of them in the span of A union B. And of course, the span of A union B is a subspace, therefore little x belongs to it. And that's the other inclusion. So I've proven indeed the equality stated in the previous to last point here. Now, let's look at inclusion to conclude this theorem. So, since A intersect B is a subset of A, the span of A intersect B must be a subset of the span of A, and that is by monotonicity of the operator, that is property 5 here. The same applies, of course, if we switch the role of A and B. Therefore, the span of A intersect B is also a subset of the span of B. It is therefore the subset of the intersection of, it is a subset of the intersection of the span of A and the span of B. Let's now look at an example of an application of our theorem. So here is a set A inside of R square containing two vectors. I claim that we can calculate the span of A using the theorem above. The way it works is you write the span of A as the span of the union of two singleton, namely the singleton 1, 0 and the singleton containing 0, 1. And, well, we have by the theorem above that the span of a union is the sum of the span. So the span of A is the sum of the span of the vector 1, 0 plus the span of the single vector 1, 1. But a few slides ago, we calculated what the span of singleton is. So we apply this here, and we see that the span of A turns out to be the set of all possible vectors in R square. So in particular, A is a spanning set for R square. We only use the properties of the theorem above. And in fact, if you kind of follow my reasoning, you can generalize that a tiny bit. So I'll let you do that exercise. Prove that for any finite family of vector space, of vectors in a vector space V, the span of that finite set is given by these expressions where you sum multiples of all the vectors x1 to xn. We will return to this problem in a few slides in a greater level of generality. I'm going to also make a remark. This inclusion, the span that is highlighted in red, that is the fact that for any two subsets A and B of V, the span of their intersection is a subset of the intersection of their span, cannot be improved to an equality. There are counterexamples. So I'm going to reuse what I observed in the previous slide. You let A be the pair consisting of the vector 1, 0 and the vector 0, 1 in R square. And you let B be a singleton consisting of the vector 1, 1. So we know how to calculate everything here. We know how to calculate the span of the intersection because the intersection of A and B is empty, and so the span of the empty set by the theorem above is the singleton 0. We also calculated using that same theorem that the span of A is R square. And from a couple of slides ago, the span of a singleton is also something we know, so the span of B is a diagonal in R square. So if you intersect span of A and span of B, it's a quick calculation. You simply get the span of B. And since the span of B contains a vector, for instance, 1, 1, well, it is not equal to the singleton 0. That proves that the intersection of the spans is possibly larger, or certainly not generally a subset of the span of the intersection. Another very, very easy application, but it's nice to see nonetheless. What if I wanted to calculate the span of V? Well, it's of course V, but there are two obvious ways to see it. I mean, one easy one is you can use the property above to note that V must be a subset of its span, and of course the span of V is a subset of V as a subspace of V, so we have the double inclusion right there. Or you could do another one. You could say, well, V is a subspace of itself, and the span of any subspace is, in fact, that subspace. So we have different ways to understand this now. So those are very abstract properties of the span. We actually don't have a good description of the vectors inside the span of A at the moment. We only know basically the first bullet point up there, that the span of a subset A is the smallest subspace of V containing A. And we can deduce all sort of properties from that single blue highlighted observation. And we can already use that to do some calculation. For instance, you have done as an exercise the calculation of what the span of a finite set of vectors must look like. Before I give an explicit description of the vectors in the linear span of a set, I'd like to show you that the collection of all subspaces of a given vector space is a complete lattice. A complete lattice is a set E with an order relation such that every non-empty subset of E has an infimum and a supremum. First, let me extend the notion of sum of spaces to arbitrary collection of spaces. If P is a collection of subspaces of a given vector space V, then the sum of P is simply the span of the union of P. We've just seen that the span of the union of two sets A and B in a vector space V is the sum of the span of A and the span of B. This notion here of sum for arbitrary collection thus extends without ambiguity the notion of sum of subspaces. I can now prove the following. If P is a non-empty collection of subspaces of a vector space V over a field K, then the sum of P is a supremum or least upper bound for P, while the intersection of P is a greatest lower bound or infimum for P among all subspaces of V, that is, in the set of subspaces of V ordered for inclusion. Do note that if you looked at P simply as a subset of the power set of V, then the supremum would simply be the union of P. but the union of P may not be a subspace. So when you work in the set of subspaces of V ordered for inclusion, the least upper bound does exist, but it is the sum of P, or in other words, the span of the union. Let's prove this theorem. First of all, I'm going to check that the intersection of P is indeed a lower bound, and that the sum of P is indeed an upper bound. So I take an arbitrary W in P, and I know that by definition the intersection of P is a subset of W. So in other words, the intersection of P is less or equal than all the elements of P, and so it is a lower bound. On the other hand, if W is an element of P again, W is a subset of the union of P. But the union of P in turn is a subset of the span of the union of P, in other words, a subset of the sum of P. So every element of P is less or equal than the sum of P. The sum of P is an upper bound for P. Now, let L be some subspace of V. That's a lower bound for P. That means that every element of P is a superset of L. Well then, of course, basic set theory tells me that L is in fact a subset of the intersection of P. So the intersection of P is the greatest lower bound of P among all the subspaces because it is itself a subspace. We have shown that as our first slide for the lecture of today. But on the other hand, if you have an upper bound for the collection P, that is a subset L, actually a subspace I should say, my mistake, a subspace L of V, which contains every element of P, then, well, first of all, as a subset, it does contain the union of P. That is true. But more interesting for us is that the sum of P, which is the span of the union of P, must be contained in the span of L by monotonicity of the span operator. But in turn, the span of L is simply L because L is a subspace. So we have shown that among all the subspaces, the sum of P is indeed less or equal than any possible subspace upper bound to my collection P, which concludes the proof that the sum of P is a supremum for the collection P. That's a little nice result, that we have this complete lattice structure on the collection of all subspaces of a vector space. All right. We've described the span of A in what you could call a top-down approach. Okay, it's a very abstract object. It is the smallest subspace containing A. That's what the span is at this moment. And we know a lot of properties. We already have gone quite far with this notion. But now I'm going to give you a bottom-up approach where I'm going to describe what are the vectors of span of A, so that we can recognize directly a vector as being or not a member of span of A for any subset A. This involves the very fundamental notion of a linear combination of vectors. So let A be a subset of a vector space V. Let K be my scalar field. A linear combination of vectors in A is a vector of V of a very specific form, namely it's given as T1 V1 plus T2 V2 plus etc. plus Tn Vn, where T1, T2, etc. Tn are scalars, and V1, V2, etc. Vn are elements of A for some natural number n. So, in other words, a linear combination of vectors in A is simply the sum of scaled vectors from A. What we are going to prove is that the subspace span of A, generated by a non-empty subset A of a vector space V, is in fact the set of all linear combinations of vectors in A. The proof of this theorem involves an interesting strategy. Let L be the set of all linear combinations of vectors in A. I wish to prove that L equals the span of A. What I'm going to do is first prove that L is a subset of the span of A, so one inclusion. But then I'm going to prove that L is a subspace of V containing A. And from this I will deduce that the span of A is actually a subset of L, and having double inclusion, I will be able to conclude my theorem is true. First, let's prove that L is a subset of the span of A. If X is an element of A, then 1 times X, which is a linear combination of vectors in A, which is simply X, is in the span of A. After all of A is a subset of the span of A, as we well know. Now assume that for some natural number n, not 0, for any collection v1 to vn of n vectors in A, and for any n scalars t1 to tn, then the sum from j equals 1 to n of tj v sub j is in the span of A. So all linear combination of n vectors with n scalars are in the span. Then let v1 to vn plus 1 be n plus 1 vectors in A, and t1 to tn plus 1 be n plus 1 scalars. By associativity, what I can do is, if I calculate t1 times v1 plus etc. plus tn plus 1 times vn plus 1, I can group the first n vectors together. That gives me the sum of tn plus 1 times vn plus 1 plus this big expression here with n vectors and n scalars. But my induction hypothesis tells me that indeed t1 v1 plus etc. plus tn vn is in the span of A. And certainly v sub n plus 1 is an element of A, therefore an element of the span of A. And the span of A is a subspace. So if I do some vector of span of A plus a scalar multiple of another vector of span of A, I get a vector in span of A, as claimed here. So by our induction hypothesis, we've proven indeed that L is a subset of the span of A. Let's now prove that L is a subspace of V containing A. I'm going to start with L contains A. So if X is a vector in A, then X is 1 times X, which by definition is an element of L. So A is a subset of L. In particular, L is not empty because you can see the assumption of my theorem, the set A is not empty. Now, we use the usual characterization of subsets. Let X and Y be 2 vectors in L. I wish to show that lambda X plus Y is a vector in L for an arbitrary scalar lambda. To do that, first note that both X and Y have explicit, if slightly long, expressions. You see, X and Y are both linear combinations of vector in A, so we write them as such. The linear combination for X and linear combination of Y may involve completely different numbers of vectors and scalars. Okay? If lambda is a scalar, then lambda X plus Y is indeed given by lambda times the expression I got for X as a linear expression of vectors in A, plus the expression I got for Y as a linear combination of vector in A. And then by rearranging my terms, you see that I get a large sum of scalar multiples of various vectors in A. By definition, that's a linear combination of vectors in A, so that's an element of L. So, indeed, L is a non-empty set closed under this forming of these little linear combinations, lambda X plus Y for any xy in L and lambda scalar. So by characterization, L is a subspace of V, and it contains A. But I know that the span of A is the smallest subspace of V containing A. That's actually more or less all I know about it. But since it's the smallest subspace of V containing A, and L is a subspace of V containing A, we have the span of A is a subset of L. That gives me the other inclusion, so I can conclude the span of A is indeed equal to L. In conclusion, if A is a subset of a vector space V, there exists a smallest subspace of V containing A called the span of A. And the span of A is exactly the set of all linear combinations of vectors in A. Now, let A be a subset of some vector space V, and denote the span of A by W. W is a subspace, so the span of W is actually W itself, which is also the span of A. In general, we do not expect that there is a single set generating a particular subspace, but every subspace is generated by at least itself. So there is a very interesting question, which is there minimal subsets of a particular subspace, which are still spanning the whole subspace. And this notion, this problem of minimality of spanning sets, is related to the notion of linear independence, which is extremely important. It will be the topic of lecture 7. Because once we know what subspaces are, we can also discuss another notion and another construction of vector spaces, which is quite important, namely the construction of quotient vector spaces. And that will be actually the topic of our next lecture.